In this lecture, we will learn about sampling techniques and inferential statistics. In this course, we will focus on inferential non-spatial statistics and one-sample difference of means test. What is population in statistics? It is not restricted to everyone who lives in a particular place, as we normally think is. It can be more abstract. We can think of them as the dots that can represent any possible entity or objects. For example, they can be trees. Different colors represent different status of trees. They can also be temperature. Different colors represent different ranges of temperature. They can be elevation, snow, or clinics, and so on. The important feature of population is that it is a complete set of all possible measurements that might hypothetically be recorded, but you cannot completely measure them all. For example, you are interested in the health conditions of all trees in a forest, but due to limited research time span and human resources, you are not able to survey every single tree in a forest. What would you do in this case? We don't give up. Instead, we take representative samples to gain insights into how the data are distributed and provides a concrete measure of that distribution. And there are different methods of sampling. Like this, we can take samples from here, or here, or here. Which method do we choose depend on the research question, nature of the phenomena, or generating processes. When we sample points, lines, or areas based on their locations using a map, it is called spatial sampling. Spatial sampling is applicable for variables that are continuously distributed, such as vegetation cover and temperature. In examining patterns of disease outbreak, it does not give us much time to respond. Therefore, we need to select samples to represent the population. This is an example of systematic point sampling, in which one point is randomly selected and all other points are sampled according to equal distance. Non-spatial sampling is not related to specific locations. We may have surveyed 100 students about their preferences of activities in planning a new student center. In this case, students' spatial location is not an important factor in determining their preferences. We may randomly select students in each department to complete the survey. The goal of the sampling is to choose unbiased and representative samples of a population. Sampling bias occurs when a sample favors some segment of the target population more than others. For example, if I'm interested in the percentage of diseased trees in this population, but I'm only sampling this segment, which include almost all of the diseased trees of the entire population, my sampling is not representative. Therefore, sampling technique is essential. A common sampling method is a simple random sampling. In this method, every element of the population has the same probability of being selected. This probability equal to sample size, n, divided by the population size, the capitalized N. For example, if you want to sample 50 people from 400 people, In a population, the probability of each people getting selected is 50 dividing by 400 equals to 0.125. To generate a truly random sample, usually a random number generator is used. Excel or R both have this function. The downside of this sampling method is that it is possible to draw unrepresentative geographic sample. For example, your sampling may not capture all levels of elevation, land cover types, or locations of disease outbreak. For a systematic sampling, we randomly select a starting point. Here, we choose 2 as a random start. But the subsequent samples follow a predefined rule, like every third. Compared to the simple random sampling, systematic sampling spreads the sample more evenly over the population. However, the disadvantage is that if a population has an inherent periodic trend, we are losing the sampling precision. A silly example is to sample temperature data every 12 months to represent temperature. Another silly example is to sample the traffic every 7 days, starting on a Sunday to represent the city's typical daily traffic. Stratified sampling first divide the population based on their categories, and then select a random sample from each category. For example, if we want to estimate the employment rate of students graduated from U of T, we may first categorize students into a few departments and randomly select samples from each department. The categories are also called strata, and individuals in each strata must be very much alike. So students in the same department is considered to be a homogeneous group, whereas the employment rate in different disciplines may vary. It is also known as geographically stratified sample, where random samples are drawn within predefined geographic areas. To retain a random component but create more representative coverage compared to simple random sampling and systematic sampling, stratified sample more accurately represent the population, as each category are represented. However, the design is also more complex, therefore increase the difficulties in operation. Based on convenience, cluster sampling are used. It is often used in neighborhood analysis. We randomly select geographic area and conduct a random sample of the objects in that area. To carry out this sampling method, a critical assumption is that heterogeneous subgroups or areas are microcosms of the large population. The advantage of this sampling method is that it is cost and time efficient. However, if the clusters are too homogeneous, they are not good representations of the entire population, and in this case, stratified sampling is a better choice. Differences between stratified sampling and cluster sampling is that in stratified sampling, you divide population by grouping variables and sample from within each group. Therefore, there are less errors but more expensive. Cluster sampling, you divide the population into groups and sample from those groups. Not all groups may be sampled. Since it is based on convenience, the cost is reduced, but the errors are increased. Think about this. If you are interested in the average elevation of a city, would you choose stratification or clustering samples? Therefore, choosing a sample design is essential. However, in many cases, one sampling method may not work out well. We may also use hybrids of the 4 approaches. For example, in studying the frequency distribution of the language spoken in Toronto, we may first stratify the population by ethnic groups and cluster to pick neighborhoods, and finally select households randomly. When designing sampling method, you also need to consider possible issues. What if you are not able to collect data as the selected sample does not grant you the permission? What if your instrument is not accurate enough? If your sample is not good, your analysis won't be good either. How can a sampling technique impact the results? Let's look at this example. Some politicians may manipulate the sampling design in order to win the votes. Let's say the blue dots represent the votes for a Democratic Party, while the red dots represent the votes for Republican Party. With electoral boundary 1, 4 voting areas voted for blue, 1 is even, and 1 voted for red. Obviously, the blue party wins the election in this case. However, if you redesign the electoral boundary, you may get a completely different result with the same point patterns. In electoral boundary 2, we get 2 voting areas voted for blue, 3 for red, and 1 is even. Now the red party wins the vote. In scientific study, we should remain objective and avoid the sampling bias.